So this week's challenge is to really use Desmos in the most maximally efficient way possible. So we're going to play around with maximization. And I want you to pretend that you are a teacher, high school teacher, and you're teaching the idea of maximization. You look in your textbook and you see a problem such as this. Maximizing a product. Consider the following problem. Find two numbers whose sum is 19 and whose product is as large as possible. Experiment with the problem by making a table like the following, showing the products of the pairs that add up to 19. On the basis of this evidence, estimate the answer to your problem. Well, we are going to move into actually generating functions after this anyway, so this seemed like a good place to start. So how can we use Desmos to zazz up this idea? First of all, I like the idea of making a table, and you can actually do that in Desmos. So what we're going to do is I'm going to walk through the lesson, and then the second video I'm going to talk about how I made each of the components of the lesson. So for now, we know what the problem is. I'm going to erase the image, and I'm going to just show a table here. And in the table, you can see we have numbers like 0, 19 in the area 0, 1 and 18 in the areas 18, etc. And you can have the students generate these numbers, etc., etc. But what's actually kind of cool is you can also plot the numbers. So if you look over here, I'm going to now put in my grid, and I'm going to put in my x-axis and my y-axis. Go into projector mode. Oh, yeah, there we go. Okay, so what you've got now is hopefully that the students can see that it looked as though it was just increasing and then increasing, but then as we put in bigger numbers like 15.4, we can see it's starting to go down again. Another thing that we can do is actually add sliders to imagine what's going on. And one way to imagine the product is to think about as A is increasing, B is decreasing. As B decreases by 1 or 2, B increases by 2. So this goes 6, that's going to go 13. 5, that's going to go 14. So what this is doing is this is basically right here, just giving you right now an intuitive idea of what's going on with the numbers. The table, plotting the table here, can help you get a more vivid idea of what the function might actually look like. So let's put in the numbers here on the axes. And now what's really happening? Well, this point here, we can say, where do those black dots come from? What are they? Well, they are these numbers here. And what is y1? y1 is computed by 19 minus x1. So how do we get the area? We multiplied this function by this function. So this function here is 19 minus x, and the other function is x times 19 minus x. So again, you know, obviously with your students, you might take a little bit more time to explain exactly where that came from, but you can generate the graph here. So I've got a point here, and it corresponds with these here. So 9 comma 10, it's over here. Here's 10 comma 9, that looks like as close as we're going to get. 11, 12, and so you can see that the goal here is to link that. So the coordinate, what does this point represent? Every point on this function is related to one configuration of these two numbers. So I could have called this x and y1 or x and x2, however we want to think about it, length and width. So you can really help them understand that a lot of times kids don't understand how to make models of things because they're not realizing, well, what's changing here and what does one point on the graph represent? So linking it to a graphical representation can be really, really powerful. Another idea is that to actually imagine the product as an area. So the green area is actually representing the different coordinates. So for example, when it's 5 and 14, you can see it looks almost sort of squarish, right? And then over here, you've got 5 and 14, but the length and width. So what's happening is the problem here is that when I went to show the values here, because they're so high, the reason this doesn't look symmetric, right, is because this 5 and 14, this is 10 here, whereas this is 50 here, so the scale is different. So I'm going to hit the home button to zoom it in so that you can get a sense. If I can find that now, we can shrink it in, that will still preserve it. Now 5 and 14 are going to be there. See, now this is exactly symmetric with this. So there's 5 and 14, and there is 14 and 5. So now you can see that they're symmetric, and that makes a little bit more sense. But sometimes, you know, the scaling helps, but now we can still see it. So what we've done, one final thing is, you might want to say, well, what is the answer? What are the two numbers? Should we just settle with 9 and 10? Remember from calculus, to find, actually, because this is a parabola, you could just find the vertex, which is negative b over 2a, and that's obviously one way that you can do it. Just for fun, we're going to add the tangent line here. So now the tangent line goes with the free point. So as I move the free point, you can actually see the tangent line moving. And we know from calculus that the slope of the tangent line has to be 0. And you can see when it's 9, 10, it's positive, and when it's 10, 9, the slope is negative, but we can't get that number right in between. And that is because we have the value for a to be discrete numbers. So if I change this and take out the step, and I just leave that blank, now we can have a lot closer. So you can have decimal points here, and so you can get a lot closer to figuring out what the actual parabola is. As you probably can figure out, the parabola, because it is a product of two functions, 19 minus x. In fact, we can put that in here, right? 19 minus x, there we go. There's 19 minus x and x, then those are the two roots, x times 19 minus x. So 19 minus x has an intercept at 19, and 0 has an intercept at 0, or x has an intercept at 0. So the vertex is going to be in between 19 and 0, and right in between that would be 9.5. So when this is 9.5, that's when you have your maximum two values, because, and we also know that the largest area of a rectangle is when the two sides are equal. So this is an example of how you might think about using Desmos to create an entire lesson about maximization. And your challenge for this week is to come up, I have about 10 choices that you can choose from, where I want you to make a linked representation, and I want you to make usually it's a parabola, the function, and then so that you have a free point here that moves when you move whatever the x-axis is on your linked representation. So now in the next video, I'm going to explain how I did each of these particular components.